Okay.
It's better before this failing.
Maybe put it into your pocket and then you somehow attach it somewhere near your. Maybe even. Will it work? Hopefully. Okay, let's slowly start. We are resuming our session. First speaker after lunch, if needed, and we'll discuss about complex systems. So Jeremy is a chair of the working group 2. But as you will see, there is a lot of connection with this group with 2 hours. I have 20 minutes.
Okay. Just
And you can also use this if you want.
oh, okay. Okay. This one full screen. Yes, full screen. Yeah. Okay. Okay. Hello, all. Great that we are meeting again. Thank you, Michael, for inviting me to talk at this group meeting. I would like first to share my impression that this is really great meeting after 4 years of our action running. I think that now we came with a very strong workshop, passed through the titles of the talks, topic selections. I'm really impressed. First idea when Michael and I discussed was to search for or to explore better connections between working group 2 and working group 1. At some point, we touched the topic of complex systems, and we were thinking also to enter this topic, and at the end, this evolved to this general talk because complex systems as a topic is pretty broad, pretty general, and can affect different or actually all of our working groups. And before I start, I would like to ask you a question that you have 3 seconds to answer, since in recent years we all lost track of the time. What is the year of our action starting? And if you don't remember, I will remind you. It seems like an obvious question, but it was in 2018. And why am I asking this? Because it was so. It was only 1 year after this Nobel Prize in Physics for gravitational wave detection. And this Nobel Prize, I think that it is very important for gravitational wave community in the sense that it pushed gravitational wave research and attracted a lot of people. Now, 4 years after our Cox action running, and 1 year ago, a new Nobel Prize was awarded for one very interesting topic, and the same impression was it is another community of complex systems. All the people that I know were fascinated about the Nobel Prize, not only about researchers, which are definitely excellent, but about the topic selection. Okay, maybe a good point to mention, maybe not, but let me mention, because I guess that our diversity agent will know that we don't have any female researcher between these nice spaces, and this is objection. On the other side, we as a cost action support diversity, and we are better than this Nobel committee in this direction. Okay, so today's talk is my attempt to make closer these two topics, actually to search for the possibilities of complex systems within our cost action research. And good point to start might be to see a bit more about complex systems, because the name itself is pretty vague and pretty wide. And for the purpose of this presentation, I have chosen this governance overview. There is a very nice article on the web, you can check it, where he explains very nicely the topic of complex systems. How do we understand when the system complex is? I'm not going to go much in this direction. Instead, I will just point out to the fields related to complex systems, which can give us impression. So typically, complex system is a system which is nonlinear, which poses some kind of self-organization, adaptation, evolution, and as such, it is strongly related to system theory research, but also applicable to network theory research. And here in the center is complexity theory, which is a bit wider than complex systems, of course, depending on interpretation. But I think that this overview is good enough for this presentation. And now I want to show you few examples of complex systems. So the first one here, very nice picture that I picked up from Eagle website. They have plenty of very good pictures. Two black holes colliding. What can we recognize here? We can recognize this nonlinearity. We can recognize chaos. We can recognize space transitions. We can recognize self-organization, and few more several topics. Maybe I missed some of them. So this is the first example, starting from two black holes colliding, and we are going now towards the Earth. And the second picture is the poster of today's meeting. The first reason I have chosen this picture is because this is the best poster I have seen in my life, but not only because of that, but because in this picture we can recognize two complex systems. The first one is Earth. Earth with mass fluctuation, with atmosphere changes, with its nonlinear dynamics. Earth is a complex system. And also here, when we are thinking about network itself is a complex system, but we are not going to go in this direction today. Okay, so now we merged two complex systems, and we received signal, and signal is passed to our equipment. Equipment itself can be recognized as a complex system. So the first one, I put here the picture of interferometer, could be taken as a part of complex system. I highly recommend this talk by Matjaž Balaj. Quantum fluctuations can have been shown to affect microscopic objects. He was speaking about this in one of VG3 regular meetings. So the second one, we can see this seismic attenuator with this pendulum chain, each of them having its own nonlinear dynamics, and each of them synchronizing with another ones, which leads us to synchronization theory and theory of complex dynamics. Okay. Until we receive this, this is all of this is happening until we receive this. This is the picture from the paper of our members. Here I put just Elena et al., but several our members were in this great research. And okay, I'm not going to go one by one. So in this case, we have something different. We have a complex time series. So this is the all of the samples are interacting with another exactly due to interactions of the sources of this time series. And one example which goes in the direction of application of complex system theory to gravitational wave research is by Marco Cavaglia, who was also speaking in VG3 workshop. And he has very, very interesting ongoing research on characterization of gravitational wave detector noise with fractals. Fractals, one of the central points in complex system theory. Okay, when we are talking about this pipeline of components in our equipment, very important point is to think about causality, because the noise at one level affects the results, outcomes at another level. And I found this very nice comics. Maybe it is not so visible now, so I will read it to you. So these are two persons talking. So the first one says, pirates have disappeared over the last few centuries. Then continuing during the same time, global warming has increased drastically. And then the second person concluded, so the lack of pirates has caused the global warming. And also, we have another prima roster which is singing always in the morning when sun arises. One could conclude that sun arising is correlated to singing of roster. But the point is that apart from correlation, we have a property which is much finer. And this is causality. If an event mandatory causes another event, it has the cause can have one effect, but the effect can have many causes. And in this direction, we are automatically led to the theory of causal networks. This is the theory which is highly celebrated by Udea L. He provided very nice example about burglary alarm problem. This is about a guy who is traveling every day to the work, and once he came to the work, someone called him and told him, "Hey, your alarm is ringing at home." And then he went quick back to check, is there burglary in the house? But during his way back, he heard on radio that there was a small earthquake. At that moment, he concluded, oh, okay, it is not burglary, it is earthquake that triggered alarm. And this is actually the first scenario given in these 3 points. So call is there, it is caused by alarm, and it is caused, we suppose that it is caused by bug. But once we are given the additional information about earthquake, our global picture changes. So the goal is to conclude the probability that burglary is really in the house if we are given all of these samples. And here we can think also about analogy, keeping earthquake as the same topic, taking into account that we have very strong research within our action on early warning systems, which deals exactly with earthquake characterization. And here we can think about burglary as about gravitational wave itself. Here I listed one by one for all of 3 hour working groups the tasks. Okay, I was suggested by Luigi, because we had an opportunity to discuss this presentation, that it was maybe better to go with our version of the task from the website, because our task evolved over time. But nevertheless, I kept this from Memorandum of Understanding with an idea to remind ourselves what was an initial idea. And here, for example, when we take a look to task 2, we have to design, of working group 1, to design machine learning pattern recognition techniques to identify non-stationary spectral lines and non-stationary noise sources. So immediately in this task, we are already in the field of complex systems. Similarly, in the working group 2, we have several points related to the seismic noise, which is itself complex series. In one of the first slides of this presentation, we mentioned that Earth itself is a complex system. And more specifically, when we are talking about seismic series, we have several open challenges. One of them is to consider them as long-range correlated signals. The second one, to consider self-organization in complex seismic time series. And if we are going more deeply into the physics, we could search for physical interpretation of seismic components of the signal from GW detector, and to study them by, for example, nonlinear Fokker-Planck equation, and decide to consider the drift and diffusion terms as a way to characterize fluctuation of the seismic time series. And finally, in working group 3, we can recognize control techniques as our great colleague Fabio Bonsagnaro told once that gravitational wave detector is one big robot. Further tasks that could be considered closely related to our action and also to complex system research, also our black hole thermodynamics. Some experiments have shown that aerial can be confirmed, although it is still discussed in the community, but the usage of machine learning techniques remains an open question. The second point is statistical physics of non-equilibrium processes, both for modeling of Earth and equipment. And finally, advanced information and learning methods for the equipment control that will be touched later at one point. What is also very interesting that physics of phase transition and emergency, we will have tomorrow very nice talk by Philip, although related more to applicative side of these issues, but nevertheless we are here. We can talk about applying our techniques to modeling of complex systems. I would like to start with the talk here, but I hope that we can continue discussion. I grabbed just several points. Intention of this talk was to open the question, so I'm not going to go towards the direction of conclusions, and I would like to thank you for your attention.
Are there some questions or comments on this one, or shall we wait for a coffee break? Okay, I think it's the time for a coffee break. Both questions. Okay, thank you very much.
Thank you.
This is really inspiring. That we have really a lot in common between the groups, so we should use that now and in the future. All right, let's move on because we're slightly late. And the second talk is from remote. I don't know how to do this. Will we have the people?
Yeah, the new speaker has to share.
Yeah. Okay. So
He's on the screen.
so I think the speaker is Daniela.
Stop sharing the screen. Okay. So.
Okay, Daniel, I hope you can hear us, and I don't know if you can hear.
Hello, everybody. Can you hear me?
Yes. Yes.
Oh,
okay.
Wonderful. Okay. So tell me when I can start.
I think yes. I think you may share your screen and basically start.
So tell me if you can see my presentation, my screen here.
Not yet.
Okay.
Now, yes.
Now, yes.
Okay. I think I just did share my screen.
Yeah, we just want to make it the full screen version of it.
Yeah. So can you see the first slide?
Yes. Yes.
Okay. Wonderful.
Just we're now working on making it really on the full screen so that it's slightly larger, but it will be okay. It's sufficiently large, I guess.
Okay.
Oh, maybe you can make it even larger. I don't know, with this plus sign, perhaps.
So it's a little cut it, but okay. I think it's now it's working.
Okay, if you don't see it well, you may always shift slightly towards the first row. Okay, then if you're ready, please go.
Yeah. So thank you very much, and thanks for scheduling me this time slot in the G2Net meeting. And I'm right now connected from the National Lab of Legnaro in Italy, and I really apologize for not being there in presence but unfortunately, when we moved the schedule of our workshop to 11 and 12 and 13 of April, I didn't really realize that I had already a workshop scheduled in the same days, and I'm not allowed to participate in this workshop where I am participating now in remote connection because I am one of the conveners of the workshop. So for right now, I am sorry to see all of you online, but I hope we can see each other in person in the near future. So my talk is to summarize part of the work that our student Francesco Barone, Professor Russo, and I have done in the past months in the framework of detecting gravitational waves in real time with some extremely low computationally complex procedure which exploits the know-how of speech processing that can be found, let's say, in published papers in the literature and in a number of tools which are readily available in the literature. So I would like to start from just some little bit of background that we have heard as well during the rest of the meeting, and that we will probably listen to. So I will just go very briefly through that. So we know that we are now in the second generation of ground-based interferometers for gravitational waves, and we are approaching even to the third generation in the relatively near future. And we know that these kind of instruments are particularly sensitive and are reaching even higher level of sensitivities in the near future, and they are able to probe a very large volume of our space and an extremely large volume of astrophysical parameter space of interest. So one of the greatest challenges in this kind of physics, which is somehow at the boundary with high performance computing and high throughput computing, is that of reaching somehow the detection, let's say, of enhancing the detection capabilities of modern algorithm in order to be able to tell, let's say, on a real-time basis whether we see or not a possible signal candidate for a gravitational wave, and possibly in the future even trying to approach a sort of astrophysical parameter estimation directly in real time. That would be an extremely challenging goal that could be desirable in the era of multi-messenger astronomy. In this framework, of course, artificial intelligence approaches are extremely promising because they can certainly accelerate the search for gravitational waves, enhancing the sensitivity of state-of-the-art algorithms for the detection of gravitational waves, and they are ideal as well to produce computationally convenient algorithms and methods to investigate interferometer data in real time. For the part of detection of gravitational waves and possibly parameter estimation, there are a series of interesting works published in the literature in recent years, which are mainly based on deep neural network algorithms, typically based on convolutional neural networks. Convolutional neural networks have been proven to be very convenient approaches to detect possible signal of gravitational waves, even in online application. However, we have to say that the applications of these particular algorithms in case studies in which we have a continuous flux of data, such as the case of a real interferometers, is, let's say, relatively challenging, because typical algorithms, at least to the best of my knowledge, that have been published exploiting convolutional neural networks typically rely on some fixed length, let's say, segments of data which are identified as potentially containing our gravitational waves or as noise only frame of the interferometer. And therefore, when you have a continuous stream of data on which you have to identify the position of possible gravitational waves, of course, the application of this algorithm is quite challenging. In order to try to somehow contribute in the field, we try to adopt a possible complementary approach than those that have been recently published in convolutional neural networks, which is an approach inspired by speech processing techniques and based on a sort of short-term feature analysis of the signal of an interferometer. This particular approach does not rely on fixed length window like typical approaches in convolutional neural networks, where they basically rely on an image, on, let's say, transforming the raw data of the interferometer in an image, either by applying a Q-transform approach or either by just putting a pixel by pixel the amplitude observed by the interferometer in an image. In our case, we look at short-term features, so we don't do hypothesis on the time length of the signal. What is the basic idea? Why do we use speech processing techniques? Speech processing techniques are used when you have an audio signals to understand regions of these audio signals which contain voice, and to distinguish regions of the audio signal which contain voice, and they are called voiced, from unvoiced sequences of a signal, where for unvoiced sequence we define something which it contains noise. These particular techniques are therefore interesting to discriminate a signal which typically lies in the region of audible, so from 10, 20 hertz up to several thousand of hertz, and even 10, 20,000 of hertz, from a persistent noise background, which is the typical goal that we want to achieve when we look at voice to unvoiced recognition in one-dimensional signals. In our case, if we look at the typical frequency regions which are relevant to our interferometer, where we can spot signals possibly becoming from typical astrophysical sources of gravitational waves that can be observed in second-generation interferometer, we see that we have a very big overlap. We are, let's say, even completely overlapped with the region where we expect to have, let's say, human voice compared to a background of noise. In the case of gravitational waves, we go from 10, 20 hertz minimum up to several hundred hertz. So we can assimilate voice, that is the target of speech recognition algorithms, as a possible signal of a gravitational wave, and unvoiced, which is the persistent noise that have to be discarded in approaches of speech recognition, as all the rest, the noise coming from the interferometer, and which is an undesired source of background for our gravitational wave study. So our goal is understanding whether an approach derived from speech processing can be used to detect in real time gravitational wave. What are the key aspects of this methodology? Certainly, this is, if it's made like that, very suitable to be applied on a continuous analysis, because typically speech recognition is based on an analysis of short-term features. and does not really rely on the a priori knowledge of the size of the sample we are analyzing and the possible position in the sample of the gravitational wave signal, is a layered approach, like all the approaches that are typically used in the analysis of audio segments in speech processing analysis. And this means that we can imagine to apply a series of algorithms of increased complexity in a sort of layered approach. Is highly modular. This means that for the way we implemented our approach, we can basically combine modules, even including different possible programming techniques. So in principle, one of the possible module of our approach, which is intrinsically based on speech processing techniques, could be even implemented with convolutional neural networks, and is as a low computational complexity, especially what I will discuss in this talk, that is what we call level 0 trigger, which is derived with the requirement to be particularly low in computational complexity in order to be suitable for application in real-time detection of gravitational wave. So very basic idea comes from this naive picture. So you have a continuous stream of data which comes from a second generation interferometer. I put there LIGO Virgo just for simplicity. To show, let's say, this is an interferometer. So we have this data stream, continuous, that is mostly dominated by noise, but time to time, very rarely, typically, we have a signal of, a possible signal of gravitational waves. The mechanism of our algorithm is that of excluding regions of the stream, which are obviously containing only noise, and therefore producing, let's say, a first zero-level trigger only in the region that possibly contain gravitational wave, with the requirement, of course, of losing the fewest possible of real gravitational wave signals. Okay, so in other words, of the high sensitivity, okay, and the requirement to try to discard as much as possible of regions of this stream which contain obviously only noise. And then, let's say, calling higher computational complexity triggers only on the very reduced amount of the data stream in which level the previous trigger, let's say, has given a temporary alert. Okay, so basically what we want to do is try to reduce the region of the data stream where we have to look for gravitational waves, and we do that layered succession of triggers of increasing complexity. Level 0 trigger is the trigger that has to deal directly with the data coming from the interferometer, and is the one which is required to be extremely low in computational complexity. Higher level triggers can even be more computationally complex because they have to be called, let's say, only on a very much reduced amount of the stream of data. So level 0 trigger is itself a layered model. It is based on the predictions of what we call the ground model, and in the next slides I will tell you the way how we decided to derive the ground model. But as you see, it is only one of the possible choices. In general, any possible model made with any possible algorithm and technique, including artificial intelligence or other programming techniques, can serve as to perform the ground prediction on which we rely. But what is a ground prediction? So basically what we have here is a typical stream of data, let's say, that is coming from the interferometer. What we do is to analyze this stream of data in small frames that we call typically mini frames, okay? So, for example, the red one is the first mini frame, and then we go ahead with the second mini frame, that is the green one, which has an overlap with the first mini frame. So for each mini frame in which we subdivide the data, we perform a ground prediction, that is this Y1 placed in the first layer of our 0 level trigger. This is called ground prediction, and is the first prediction made by an algorithm on which the rest of the framework, the rest of the level 0 trigger relies on. Second layer of the level 0 trigger takes the ground prediction made by the ground model for each mini frame, okay, and try somehow to extract the possible position, okay, of a gravitational wave which could be located into this noise of the interferometer. As soon as we understand where the possible gravitational wave is located, then we issue a ground, let's say a level 0 alert that goes to the subsequent layers of the framework. But what the ground model contains, or based on what the ground model gives us an output on each individual mini frame in which we reanalyze the data. So the ground model in our case is a model which is derived with machine learning, with a supervised learning approach, which tells within each mini frame in which we subdivide the data whether we do expect or not a gravitational wave signal in the mini frame itself. Okay, so to derive this kind of model, which is just an example of a possible model that can serve as a ground model, we prepared a set of simulated gravitational wave events, and in which, for comparison with the literature, we simulated a series of binary black hole merger events. So we are focusing exclusively on gravitational wave signals generated by pairs of black holes merging in synthetic noise of the instrument. And of course, we know that the noise of the interferometer is extremely complex to characterize, but as a first, let's say, validation of these possible features that I will present later, we decided to generate a Gaussian noise, which is the simplest possible example of noise, and generating a Gaussian noise allows us as well to compare in a more suitable way the results of our algorithm with previous results of similar algorithms that were published in the literature so far, and that have been focused exclusively on understanding the presence of a gravitational wave in a Gaussian noise characteristic of the instrument. So we generate two possible types of patterns. Patterns which are made by noise only, okay, extracting, let's say, a noise time series according to the design sensitivity curve of LIGO in this case. So we have focused on LIGO to have a better comparison with the literature, and then similar noise sample that contain a Gaussian noise according to the LIGO design sensitivity, in which we sum at a given signal to noise ratio a possible signal of a binary pair of black holes. So we have noise only sample that we label with 0, and noise signal plus noise sample that we label with 1. And the ground model is the model that will tell us if a certain mini frame is a 0 mini frame, so if it contains noise only, or is a 1 mini frame, so if it contains suitably signal plus noise. Signals that have been generated are binary black hole merger signals comprising in spiraling, merger, and ring down phases of the binary black hole merger. They have been simulated with some state-of-the-art simulation tool, typically adopted in the literature, and several astrophysical key parameters were randomized in order to probe the accuracy of our approach on a various set of astrophysically relevant parameters. So the mass of the first partner was randomly chosen between 5 and 100 solar masses, and the second mass was chosen such as that the sum of the masses was, let's say, within 100 solar masses. The way how we extracted the mass M1 and M2 of the two pairs, of the pair of two black holes, follows a canonical logarithmic mass distribution, which was recently proposed in the literature. Then we have a randomly generated inclination angle according to a sine distribution, a phase generated randomly according to a uniform distribution, a random polarization angle, a random sky location of the gravitational wave in the sky, which was extracted according to a uniform distribution, and we get something that looks pretty much like that, the typical chirp of the binary black hole merger gravitational wave waveform. But then we have to generate noise. Noise, as I said before, was generated according to some assumption to some recent LIGO design sensitivity curve, which included all typical sources of noise of the real interferometer, and this allows us, in the hypothesis, of course, in the very simplified hypothesis that the noise of the interferometer is Gaussian, okay, allows to generate typical samples which contain noise according to the sensitivity of the instrument. At this point, in order to create this signal plus samples that will be used in order to train the artificial intelligence approach that we adopted to derive the ground model on which the whole level 0 trigger will rely, is done as follows. So we have a series of simulated signals, a series of simulated noise samples. That's just basically sum signal plus noise, but again, we have a various possible signals coming from different astrophysical sources with different parameters, but we want to subdivide them into a meaningful set that we can use to derive our model. So the key information is the signal to noise ratio. Okay, we expect our algorithm to have a signal to noise ratio dependent performance, because obviously a certain astrophysical source placed at a certain distance will produce a given signal to noise ratio, but if we put it further at a further distance, then we will have a lower signal to noise ratio. So the key point for us is putting together signals that have the same signal to noise ratio in order to test, let's say, the performance of our algorithm as a function of the signal to noise ratio. So we scale the signal in order to have a target signal to noise ratio, and we adopted signal to noise ratios varied from, I think, about 6 up to about 15 this is the region where we, let's say, varied our signal to noise ratio, where for signal to noise ratio, I intend the optimal matched filtering signal to noise ratio, okay? So the signal to noise ratio in the sense of matched filtering. So after that, after summing the signal suitably scaled at the desired signal to noise optimal matched filtering signal to noise ratio, and adding the synthetic noise produced by the simulation of the interferometer, we widen the whole time series. And at the end, we have a set of widened signals that are used as the input for our ground model. So as I said before, we have a certain data segment, and for simplicity, we use 1 second length data segments for this specific application. This is for having a better comparison with the literature, because previous convolutional neural network approaches focused on 1 second length time series, and this is also justified by the fact that the relevant part of the waveform of two black holes merging, let's say, it goes, let's say that the relevant part of this signal which enters the sensitivity of the interferometer lasts typically way less than 1 second, 1/10, 2/10 of a second, or something like that. So 1 second is a safe margin to contain the relevant part of a waveform coming from a binary black hole merger event. So in this 1 second is suitably subdivided into small regions, which, as I said before, are called mini frame. And for each of these regions, we calculate a series of features inspired by speech processing techniques. These features include a series of information such as zero crossing rate and a series of other information, and include a lot of filters which are typically used for speech processing techniques, such as cepstral coefficients and other things like that. There is a list of possible features and where we extracted and from where these features were extracted in a draft that I circulated recently to with the G2Net group. But the relevant point here is that we have around 1,840 numerical information with which we feed our machine learning algorithm to derive the ground model. So for each mini frame, we have a high dimensional feature vector of 1,840 feature. We feed with this 1,840 feature the brain project, which is a tool for formal modeling of data, which is based on neural genetic programming. In other words, is a tool which comprises a genetic part which foresees the evolution of tree-like structures suitably representing mathematical expressions, and use artificial neural networks as a so-called hill climbing operator in order typically to optimize the numerical constants of each mathematical expression. So it combines these two aspects, the genetic part to perform a sort of global search on all the space of the models that can describe our data, and the hill climbing operator, the neural part, which performs a sort of fast local search in the proximity of a minimum of the error function that we want to minimize, for example. The interesting point of this algorithm is that it is capable of performing a very accurate feature selection. So we start from 1,840 feature, and we end up with a model which has an analytic expression, as you can see here, and this makes it very suitable for online application because you just need to calculate a formula. And at the end, this model, without so much lack of performance compared to what you can obtain if you have available 1,840 features, end up with only 4 of those features. So the feature selection approach, which is based on the Darwinian evolutionary theory, which is based on a sort of implementation, artificial implementation of the natural selection, selects only 4 of these numerical information to serve for representing the information, whether we have or not a gravitational wave in this data stream, in each mini frame. So at the end, you see that this model is extremely low in computational complexity because it needs exclusively 4 numerical quantities to be calculated, that can be even calculated in parallel, and the application of this simple formula that you see here for each mini frame. Just to tell that each mini frame has a duration of 100 milliseconds in our approach, but also this is a possible parameter that we can vary. So at the end, we can analyze what is the output of the ground model for a series of mini frames in a 1 second length data segment. Okay, as I said, the reason why we are fixing the length of the data frame to 1 second is for a better comparison with the literature, but we don't have any assumption on the length of the data frame or on the position of the gravitational wave within the data frame in our approach. So as you see, if we have 100 milliseconds mini frames overlapped by 50%, we end up with 19 mini frames. Okay, so we subdivide 1 second of data, which can contain or not a gravitational wave signal, in 19 mini frame. For each mini frame, the ground model calculates a number that is here in the y-axis. So this is the output of the ground model. As you see, the output is a continuous variable, which ideally approaches 1 when we are in the presence of a gravitational wave signal, and approaches 0 when we are in the presence of a noise-only mini frame. As you can see, if we look at the evolution of the output of our ground model for these 2 data segments, the left one containing a signal, let's say the center of the signal is around mini frame 15 in this case, so the merging, let's say, the moment of maximum amplitude of the signal, and in this case we have a noise only 1 second duration sample. The interesting fact is that we have an average higher value of output typically when we deal with signal plus noise sample, and with this we like, because on average this 1 second sample is let's say, a positive output of our algorithm, and we have a lower average value in the case of noise-only sample, and typically in the proximity of the maximum of the gravitational wave waveform, we observe a series of output values which are well above the average, and this allows us to perform a first possible interpretation of this model output, which we call thresholded model. What is the way how we interpret the output of the ground model? So we put a threshold, which obviously is regulated according to optimizing sensitivity and specificity of the classifier, and we call 1 all the mini frame which are above threshold, and 0 all the mini frame which are below threshold. And we end up having, in the case, for example, of a typical noise plus signal example, a series of 1, let's say a cluster of 1, typically close to the peak of the gravitational wave, while in the case of noise, ideally all 0, in reality, mostly 0, and sometimes something which goes ahead of the threshold, above threshold, but typically an isolated 1. And then we can perform a clustering analysis on this output and tell whether in a 1 second length frame we have a gravitational wave or not. This is called, as I said, a thresholded model, and we can use sensitivity and specificity to analyze the quality, the accuracy of our algorithm, where sensitivity is the fraction of the gravitational wave samples which are correctly identified as gravitational waves, and specificity is the fraction of noise-only samples which are correctly identified as noise. As you can see, it's very nice to see that increasing signal-to-noise ratio, we increase the performance, and already above, let's say, signal-to-noise ratio 12, the performance is very high. At signal-to-noise ratio 14, for example, if we go at specificity above a 1 minus specificity, so at a false alarm rate, let's say of about 10 to the minus 2, we already have over 90% of of gravitational wave signals correctly classified as gravitational wave signals. Our approach is very versatile. We can improve even a little bit better this kind of interpretation if we don't apply any threshold. So if we take the raw value as they are produced by our initial ground model, okay, we can apply a sort of multi-modeling procedure. What I mean for that? I mean that we take the continuous output, we calculate additional features on the continuous output, such as the average value of the output, the slope of this output, the standard deviation, and a series of other features. We calculated over 100 possible features, and we do a second analytical model, again for the BRAIN project, to infer whether a 1 second sample, according to the prediction of the ground model, contains a gravitational wave. In this case, with the dashed lines, I put the sensitivity and specificity curve for the thresholded model, the one that I discussed before, and same color, but with a continuous line, I see the performance of the unthresholded model, of this new model, to interpret the output of the ground model, which doesn't use a threshold. As you see, for the same signal-to-noise ratio, we have a very nice increase in performance. So you understand that the ground model contains suitable information, and depending on the way how you interpret this information, you can obtain different possible performance. At the end, you see that for signal-to-noise ratio 12, the performance of the unthresholded model in identifying gravitational wave is almost saturated to 100%. You see that only a very small false alarm rates, you have deviation from about 100% of gravitational waves, but it's almost always above 80%. And this is just the last slide to compare our results of this level 0 trigger for right now with the literature. In this slide, I summarized the result of convolutional neural networks at signal-to-noise ratio 6 and 4, and matched filtering at similar signal-to-noise ratio. These blue dashed lines, this light blue, are the convolutional neural networks. So light blue lines, convolutional neural network, dark blue are matched filtering, and red lines are our model. So as you can see, if we go at signal-to-noise ratio 6, the unthresholded model obviously has a performance lower than convolutional neural networks and more complex match filtering, but not so lower, I would like to say, even though we exploit only 4 features. For example, if we go at a false alarm probability 10 to the minus 2, we are able to correctly identify about 30–40% of gravitational wave signals, while state-of-the-art convolutional neural networks and match filtering perform with about 60%. Okay, so they have a better performance than us, but not so dramatically better if you consider the amount of features of numerical information we use, which is only 4, and if you consider that we are based on a very small and easy to interpret and implement analytical formula. And another point is that this kind of analysis is based on fixed length segments, which is an ideal condition for the convolutional neural network, but is a totally not ideal condition for us, because we don't have any assumption on the length of the window or on the position of the gravitational wave within that 1 second of data, which is instead exploded in convolutional neural networks. So to conclude, I would like to say that applying this short-term analysis, including analytical formulas, is possibly promising because allows to with a very relatively good performance to probe the presence of gravitational waves with a low computational complexity, which is suitable for real-time application and low latency application. But of course, some improvement has to be made in this respect, and we are already working on that, and we believe that we will improve drastically the performance of this algorithm, of this model, if instead of considering information from isolated mini frames, we consider information from consecutive mini frames. In this case, beside the information on the amplitude of the signal, which is what we are exploiting at the moment, we will be able to exploit information about the time evolution of amplitude and frequency of the signals, which will improve our performance. Okay, so thank you very much, guys, for your attention.
Very much. We are exactly at the time of our coffee break. So, so maybe the one short question. Yes. Okay. Is there a question? Okay. Okay.
Ciao Daniele. So in the last slide, could you share again your screen with your last slide? So there was a plot with the signal to noise ratio was 6 and 4. Sorry, I'm a bit back in the room.
Yeah, I didn't comment fully this picture because I got all the available time. Yes, we considered 4 and 6 as signal to noise ratio.
You mean 4 in the sense only 4 or greater than 4?
No. Signals with exactly 4 as the signal to noise ratio.
And why you just have 4 and 6 and not like 8, which I would have considered like more obvious?
Yeah, I agree with you. And actually, in 8, the gap in performance between us and the convolutional neural network is even lower than that. So we almost reach convolutional neural network if we increase the signal-to-noise ratio. The reason why I used 6 and 4 is because these guys of the convolutional neural networks gave us results only for 4 and 6, and I didn't simply have access to results at 8. So that's it. Yeah. I agree with you.
Okay.
I guess from the voice you are Agata, right?
Sì, Daniele,
okay.
Sì, sono io.
Yes. Ciao, Agata.
Okay, other questions? Okay, so no questions.
Hi, Daniel. Here is Radomir Milic. Thank you for a very interesting presentation. My question is about the nature of noise in speech and noise in gravitational wave data, and similarly the nature of gravitational wave signal and nature of speech as a signal. Do we assume that there is some analogy so that we can apply the same techniques? Because I'm concerned that these noises are of different nature.
Okay, so thank you very much, Velimir, for the question. That's actually a very nice question. The whole idea is based on an analogy, and the analogy is pretty much, let's say, in the frequency domain. I had to say almost an analogy because if you see the typical frequency range of the voice, that's typically kind of higher than the frequency domain of gravitational wave signal. So there is even, let's say, these two ranges are overlapped, but they are not exactly the same. So we are doing the assumption that speech processing features, let's say, that are useful for voice and unvoiced could serve also to probe gravitational waves, which are indeed at a lower frequency typically compared to the voiced signal. Then also the nature of the noise is completely different, but what we have used so far, as you see, is even a noise which is not that realistic for an interferometer itself, because that's an assumption of stationary noise, let's say. So I agree that we should definitely work out on the noise to include in the near future also other sources of noise. But again, the assumption is that the noise typical of the interferometer can be treated as the noise like in the speech recognition. Okay, so the idea is to have an analogy, even though this noise has a different nature.
Okay, thank you very much.
You're welcome.
Thanks. Okay, so now, Nicola, are you on the remote side? Because we have still the one talk before the coffee break, and now we are thinking maybe about if this would be okay with you, Nicola, to have a talk after our coffee break, which is 4:15, or would you prefer to give it now? And because, for example, you don't have time later.
It's the same for me. If you want to have a coffee break, I can talk later. It's however you
All right,
want.
so we will stick to the original schedule and have a coffee now, and we will come back quarter past 4 for your talk. Thank you very much. So it was not a very good German today, but okay. So
Okay.
we will be in 20 minutes. Thanks.
Perfect.